Welcome back. So in the last lecture, we introduced how to approximate derivatives of a function f with respect to t, df dt, using these finite difference derivatives. So instead of taking the limit as delta t goes to 0 in the normal definition of a derivative, for lots of reasons, if we want to compute this on data or we want to compute this for a function but on a computer, we often drop the limit as delta t goes to 0 and instead use this approximation for a finite but small delta t. And so we cooked up a few different schemes that will all approximate this first derivative df dt. And we saw how the error of those different approximations behave based on these Taylor series expansions of f of t plus delta t, f of t minus delta t, and so on and so forth. So when you plug these Taylor series into these approximations, you find that your forward and backwards difference schemes have error that is on the order, kind of the leading error term is on the order of delta t. And the central difference scheme is more accurate, so its error is on the order of delta t squared. So if I want better accuracy of these methods, I have to make delta t smaller. But if I make delta t 10 times smaller, these methods only get 10 times more accurate, whereas central difference gets 100 times more accurate. So pretty cool, okay? And so you can actually cook up even higher order accurate schemes. So you could cook up an order delta t to the 4th or 6th or 5th or 3rd or whatever your heart desires. So I would, we use these Taylor series expansions. So I'm just going to point out that you can actually come up with a higher order accurate approximation for df dt using more terms instead of just f of t plus delta t and f of t minus delta t. You could add f of t plus 2 delta t and f of t minus 2 delta t. And you'd go through the whole kind of expansion, dot, dot, dot. I'm not going to write it out here. And so this is actually a great homework for you. So this is a homework I would assign my students in my class, is what you can do is write out this Taylor series expansion for f of t plus 2 delta t and f of t minus 2 delta t. And then see, just like what we did in central differences, we tried to isolate this f prime of t, the thing we wanted, df dt, while killing as many terms in the Taylor series as possible above it. So we wanted to, kind of push our error out as far as possible and as high of a power of delta t as possible. And so with these two terms, this was as good as we could do. That's as many terms as we could. We basically killed these second derivative terms, and our error kind of came out into this delta t cubed f triple prime term. So when we divided by delta t, we got an order delta t squared error term. What I claim is that if you expand these Taylor series in pink here, with those 4 equations, you'll be able to get an expression, kind of a central difference, but with 4 points instead of 2 points. You'll be able to cancel not only these terms, but you'll also be able to cancel more terms in your Taylor series. And I claim you'll be able to push this error to an even higher power of delta t. So that's a really good exercise. Try to use these terms here to cook up an even higher order accurate central difference scheme using all 4 of these terms to push this delta t. I think you'll be able to get it probably to delta t to the 4th power. That's my guess. I'm not 100% sure. I haven't done this in a while. It'll definitely be higher than delta t squared. Similarly, you could build a higher order finite difference with only forward terms. So you could only use f of t plus delta t, and f of t plus 2 delta t. And again, you could use just those 3 terms and come up with something that's order delta t squared. Same with backwards difference. You could use only f of t minus delta t, and f of t minus 2 delta t, and cancel out terms in your Taylor series to get something that's order delta t squared. So that's an excellent homework set for you. You'll get really good at both, expanding the Taylor series, manipulating these terms, and you'll really understand what this error accuracy means. Okay, so highly recommended to do that. You can also approximate second derivatives. So maybe I'll do that right now. So I think what I'm going to do now is I'm going to show you how to do the same thing, but for computing the second derivative, d squared f dt squared, by using finite differences. And then we're going to talk about how to approximate these on actual data vectors. So in the last video, I showed you how to do this with, if you actually had access to this function f, if it was like a real analytic function like sine or cosine. But now I'm going to show you how to do this if someone emails you a data set. How do you compute the derivative? Or if you're measuring the path of a comet or an asteroid in time, how do you take the derivative of that position in time? For example, when I don't have access to f of t plus delta t. That's the future. I don't know the future, so I only have these past measurements. How do I do that? Okay, so that's all coming up in this lecture. Good. And so maybe I'll just start with the second derivative, and I'll start with the definition. So the definition of the second derivative, second derivative is d squared f dt squared. And again, we could write this as the limit as delta t goes to 0 of my first derivative, f prime, evaluated at t plus delta t minus my first derivative at t divided by delta t. And you could take that limit as delta t goes to 0, and then this would be the honest to goodness second derivative. But again, as we did here, you could drop this limit and just take this finite difference to approximate d squared f dt, the second derivative. And so you could take f prime, you could approximate f prime using one of these schemes, and plug in t plus delta t to that approximation. And you can approximate f prime at t, again using those schemes, and plug. So I would recommend if you use one of these approximations for f prime at t plus delta t and f prime at t, try using the same scheme to begin with. So you could use the forward difference pink scheme for f prime of t plus delta t and the forward difference pink scheme for f prime at t. And if you plug that in, you'll get kind of a forward difference approximation for the second derivative of f with respect to t. And so that's actually another good exercise is, like try this approximation for f prime and then see what the error approximation is, see if it works. Try the same thing for backward difference, try the same thing for central difference. Try a different scheme for this f prime and a different scheme for this f prime, and I don't think it's going to work as well. It might not work at all, okay? But that's not what I'm going to do right now. We're actually going to construct an approximation of this d squared f dt squared, just like we did before, by trying to take some combination of these two Taylor series so that we isolate the term we want and kill as many of the other terms as possible. Okay, so what we want to do is we want to isolate this f double prime of t. F double prime literally means d squared f dt. We want to isolate this, and we want to kill as many terms in the Taylor series as possible. So the first thing I'm going to do is, it's pretty obvious that if I add these together, if I add star and double star equations, if I add f of t plus delta t and f of t minus delta t, I'm going to cancel out all of the odd powers of t, because all of the odd powers of t are going to have a minus sign. So I'm going to cancel out the f primes and the f triple primes, which seems like a really good start. And I'm going to be left with my f double primes and 2 f of t. So if I write down, just bear with me, f of t plus delta t plus, so here we subtracted them, here we're going to add them, f of t minus delta t. That's going to equal 2 f of t, which I don't want. This is just something I don't want, plus 2 of the terms I do want, plus 2 times this thing, which 2 factorial is 2, and 2 over 2 is 1. So this is delta t squared f double prime of t. That's the thing I want. All my cubes are going to cancel. So I'm going to get something that's plus order delta t to the 4th and higher, right? My cubes cancel out, so I'm only left with my 4th order delta t to the 4 f quadruple prime. Those terms are going to add up, and then I'm only going to have every even term, the order t to the 4th, t to the 6th, t to the 8, and so on and so forth. So this is actually a really good start. Again, this is the thing I want. So if I take this expression minus 2 f of t divided by t squared, delta t squared, I've isolated f double prime. So that's what I'm going to write down now, is I'm going to write down, maybe I'll do this in pink. I'll write down second derivative. And this is a central difference second derivative scheme. My second derivative, d squared f dt squared, is approximately equal. Okay, again, I'm just going to walk through this. This expression here, if I subtract 2f of t and I divide by delta t squared, I've isolated the thing I want. So this is f of t plus delta t minus 2f of t plus 2, no, not 2, just a single one, just one f, sorry, plus f of t minus delta t. And I've rearranged, when I subtracted this 2f of t, I just put it in the middle here because I kind of want to order them. This is the future point, this is the present point, and this is the past point. So future, present, past, I just kind of order them in time, but it's the same as this minus 2f of t. And then I divide by delta t squared, all of this divided by delta t squared, and that isolates my f double prime, so that's all equal to f double prime, plus my order delta t to the fourth divided by delta t squared. So that becomes order delta t squared. So plus order delta t squared. And so again, the second derivative central difference, this is central difference because the point I want, f of t, is sandwiched between f of t plus delta t and t minus delta t. So this is literally called the central difference. I approximate the derivative in the center by the points away from it. So it's in the center of these 2 points that I'm using. The central difference second derivative approximation gives order delta t squared error. So the error, so the thing I want is f double prime of t, and then all of this is the error term. And so when I divide by my delta t squared, this error term becomes order delta t squared. Delta t to the fourth divided by delta t squared is delta t squared. So really easy. Again, we can construct first derivatives using different schemes with different error accuracy. We can construct second derivatives with different schemes and different order accuracy. I could create a fourth order central difference second derivative, d squared f dt squared, again using these 4 points, not just these green points, but these pink points as well. Okay, and sometimes this is called a stencil because if you literally look at, let's say we're looking at this this curve that we're trying to take the derivative of, like this, and we have these points here. Let's say this is t. And then each point to the right is t plus delta t, t plus 2 delta t, t minus delta t, t minus 2 delta t. I'll just draw, t plus delta t and t minus delta t. And of course, this is 2 delta t and minus 2 delta t and so on and so forth. If I have data at these points, these discrete delta t measurements in time, then essentially you can almost think of, this second derivative is one of these plus one of these minus 2 of these. So, one of the f of t plus delta t plus one of the f of t minus delta t minus 2 of f of t is going to, all the Taylor series is going to cancel out, and I'm going to get the thing I want, the second derivative of f with respect to t, plus a little bit of order delta t squared error. And so these points here, you can almost think of it like a stencil, like when you're a kid and you make a stencil and you trace out a stencil. You use these 3 data points in this very particular way, and you take that combination and you get this derivative. And there are higher order stencils that use more points that go beyond. So if I want a 4th order scheme, I'm going to need to include these points in my stencil, and I'll get some combination like this, but now it'll have f of t plus 2 delta t's and f of t minus 2 delta t's, and it'll be higher order. It'll be order delta t to the 4th. So really good exercise for you to do is to really just try to do all of these. You can make almost any of these that your heart desires. You can make higher order, central difference, forward difference, backwards difference, first derivative, second derivative, third derivative, and you just need to use these Taylor series in the right combination. So really cool stuff. Good. That that's mainly what I want to show you for the first half of this video. I think for the second half, what I'm going to do is I'm going to show you how do you actually compute these things on real finite discrete data sets. So again, in the past, we assumed, this is a very small kind of subtle distinction, but in the past lecture, we assumed we had access to an actual function, and we can evaluate that function at any point in time we like. And so we evaluated sine at t plus delta t minus sine of t. But let's say I actually just have a big vector of data. Someone emails me a spreadsheet or a list of measurements, or maybe even better yet, I'm collecting measurements in time. I have my telescope and I'm measuring the position of a planet or a moon in time. And I just have the measurements I have. I'm collecting them in real time, and I want to be approximating these derivatives in real time. Okay, so I can't just query f at any time I like. I'm getting measurements of f at these very discrete punctate times t plus delta t plus 2 delta t, and so on and so forth. How do you compute this on actual data? So that's what I'm going to show you now. And I always like to think about this, why would I always use a central difference scheme, right? It's obviously better than my forward and backwards difference scheme. It is better accuracy scaling in delta t. So central difference has order delta t squared accuracy, which means if I cut delta t, if I make delta t 10 times smaller, these only get 10 times more accurate, but this one gets 100 times more accurate. So why wouldn't I always use this scheme? And at least one reason is because if I'm measuring something with a telescope, maybe I'm measuring, maybe there's a ballistic missile coming from one part of the world to another part of the world, and I want to compute its derivative and its acceleration and things like that, its velocity and acceleration. I don't know what f of t plus delta t is. This is a measurement in the future. So if I'm computing these in real time, I don't actually have access to these t plus delta t's. I only have access to t minus delta t, maybe t minus 2 delta t. So if I'm doing real-time calculations of something that's evolving in time, I'm actually kind of stuck with backwards difference derivatives. Okay, so that's one reason why I might not use the better second order central difference scheme. Another reason might be maybe, again, I actually do have access to all of those points in time. Maybe it's historical data and someone just emailed me this data. But still, at the beginning and at the end of those time points, at time 0 and at time final, at time 0, there is no f of t minus delta t. So I can't do a backwards difference or a central difference at my starting time. I have to use a forward difference at that left time point at t0. And similarly, at my final terminal time point, I don't have t plus delta t. So I can't do a central difference or a forward difference. I can only do a backwards difference at my final time. And so if you have historical data, from some start time to some end time, essentially you can do central difference in the middle, but on the left you have to do forward difference, and on the rightmost point you have to do backwards difference. So these are real practical considerations you have to keep in mind when you're doing this on data. Okay, so good. I'm going to probably erase this, draw a little picture of what I mean by data, and then we're going to code this up in Python and Matlab. All right, so just one moment. Okay, so now I'm going to show you how to do this numerical differentiation on a data set. I erased everything because I figured you probably can remember forward difference, backward difference, central difference, and if not, pause the video, try to write them down from memory, try to make sense that these are actually what they should be, and then you can kind of rewind and see if they match, and if not, you might want to, kind of rewatch that section. But here, what we're going to be doing, I'm just going to draw a nice big picture of the function that we're taking the derivative of, okay, f. And it looks like, at least in my notes, I switched from f of t, a function of time, to some function of space, f of x. I hope at this point you feel comfortable enough that the specific variables don't matter. This could be a function of time, and I could take its derivative with respect to time. This could be a function of space, and I could take its derivative with respect to space. It doesn't matter. So everything I showed you with f of t also applies to f of x. You can take df dx using exactly the same methods. If you have some position x of t, you could take dx dt in exactly the same way I showed you before. Okay, so I want you to get kind of, sometimes I switch variables because I wasn't paying attention and I forgot and maybe I got lazy. Sometimes I switch variables on purpose because I want you to have that power of abstraction and that flexibility that, it doesn't matter if I'm taking dx dt or df dx or df dt. Sometimes my function varies with respect to time. Sometimes my function varies with respect to x. And sometimes my function is going to be called x and it varies with respect to t. And in any of those cases, I can take the derivative of my function with respect to its independent variable using the methods we've talked about. So we have some function. I'll pick some cool colors here if I can do it. So I've got some function, and what we're going to do is we are going to define this function on discrete data points. We're going to have x1, x2, x3, and I'll just draw a few x4, ... all the way up to, let's say, x big N. Okay, so I've got n data points here. And I'm going to assume that these are spread apart, delta x apart. They don't have to be delta x apart. They could actually technically be unevenly spaced. I'll talk about that at the end. But for now, assume that each of these is spaced at a fixed delta x. If this was a function of t, these would be a fixed delta t. Those would be the delta t's from before. And I literally have measurements of my function. I've got f at x1. I have f at x2, f at x3, f at x4, at x5, ... all the way up to my function evaluated at fn. And so I'm literally going to call these points f1, f2, f3, f4, ... up to fn, okay? And if you like, you can say, well, fk is equal to my function f evaluated at xk, at the kth location, k equals 4, k equals 5, and so on, which is equal, in this case, to f of k delta x. Okay, I'm assuming that this starts at 0, and this is delta x, 2 delta x, 3 delta x, 4 delta x, and so on and so forth. So this is just setting up some notation here that I have my data points x, and I have my x positions where my data was taken, and then f is my actual data. And so I essentially have two vectors. And I'm going to have my math over here. So I have two vectors. I have x1, x2, x3, ... to xn. That's a vector of initial positions where my data is measured. And then I have the vector of the data itself, which is my function evaluated at x1, my function evaluated at x2, evaluated at x3. And these could be, measurements from a telescope or from radar or from anything that I'm measuring in space, or in time or whatever. It doesn't really matter. And so the idea here, like I said, is that if this is a data set someone, emailed me, or I downloaded this off the web, or I'm collecting this data set, I can compute the derivative df dx. Okay, I can compute df dx, df dx. And I can use, for example, a forward difference at this leftmost point, because I don't have a point to the left of f1. That's my first point. So I can't do central difference or backward difference. I have to do forward difference at f1. So I'm going to do, forward difference at x1. Similarly, at the rightmost point, I have to use backward difference because I don't have a point past this rightmost point. I can't do central difference or forward difference. So I have to use backward difference at xn. And I can use central difference, in the middle. So I'm just writing this down to be very, very complete. This is what I'm going to do. I'm literally going to code up, a scheme that does these derivatives to approximate the derivative of f. And it's not going to be on a function f. It's on this data vector f. I'm literally going to take f3 minus f2 divided by delta x to get my derivative at that point, and so on and so forth. Okay, so I'm going to approximate my derivative at each of these points by taking the difference of these numbers now. These are not functions, these are numbers, data numbers. I'm going to take the difference of f3 minus f2 divided by delta x. That's going to give me my forward difference derivative at f2, for example. Okay, pretty simple idea, but again, I want you to feel really comfortable going back and forth from functions to data. Data is a big deal. And just before I go into Python and Matlab, I'll point out there's actually some really cool new machine learning results. So we compute these derivatives all the time when we numerically simulate physics and the real world. So if I want to numerically simulate a drum membrane or a fluid flow or a guitar string or pretty much any physical system that varies, in space or in time or in both, I'm going to be in a computer kind of evaluating numerically derivatives and setting them equal to stuff and solving for other variables. I'm going to be using these numerical derivatives in a computer. And oftentimes researchers, for example, in fluid mechanics, if you want to solve for the turbulent flow over a wing, this is a very expensive calculation, and researchers will cook up very high order accurate numerical schemes to approximate that better and better and better. With small delta x's, they want as good of an accuracy as possible, or with small delta t's. And so interestingly, researchers have recently, within the last few years, cooked up new finite difference derivative schemes, kind of new stencils, if you like, of how to use this data to approximate the derivatives at these points even better, tailored to specific problems like turbulence or like shock formation in fluid flows, using machine learning. So there's some really cool papers. There is a PNAS paper. I think Bar Sinai and other co-authors. I'll put a link in the in the description if I remember, and if not, give me a comment to remind me. But basically, they learned with machine learning. They took like really accurate data, and then they learned from that data what is a really good stencil that for turbulence, for example, approximates those derivatives especially well, or for shock formation. It's a really cool idea, kind of going beyond this Taylor series classical math. I really like that idea. Okay, good. Let's code this up. Let's try this out. I think we're ready to go, and then that'll be the end of the video. Okay, good. So I'm going to go over, let's see which one's up first. Looks like we got Python. So again, this is code written by Alan Kaptanoglu based on the MATLAB version of this code from before. So this is very similar to the code from the previous lecture. In fact, the previous lecture, the code was lecture 14, finite difference. This is finite difference 2. I'm very creative with my naming scheme. And so similarly, we're going to compute the finite difference derivative of sine of x, but we're not going to do it from the function sine of x. We're basically going to create a vector of data, and then we're going to take the derivative of that vector of data. Okay, so here we're going to basically assume we have n equals 30 data points, so n is 30, and we're going to create this kind of spacing with, I guess, a spacing of something like 0.1. Delta x is going to be 0.1, so delta x is 0.1, and we're going to go up to 30 data points. And we're going to evaluate that vector of x on sine of x. So this is going to return a vector of f values for sine of x. So we're going to plot the true function f, the clean function. Then we're going to plot the data. These are these x's. And I'm inverting my color, so these are not red x's. The inverse of red is cyan. So if this looks confusing because this should be red and it's not red, it's because I'm inverting my color scheme because I'm sticking with the black background here. And so literally what we're doing is we're computing this derivative with these blue points here. So these blue points are our function evaluated at those discrete x points. And so as we mentioned before, we have to do forward difference at the x1 location, at the first location. And Python starts its indexing at 0. So if it's again, anyone who knows Python is not going to be confused by this starting at 0. This is the leftmost point here. And at that leftmost point, I can't do central difference. I can't do backwards difference. I have to do forwards difference. So this is the forward difference. And remember, this is not sine of x plus delta x minus sine of x. It's literally f, the second f minus the first f divided by delta x. Okay, that's the forward difference. And then in the middle, for I in the range of the middle, I can do central difference. That's f at the next point minus f at the previous point divided by 2 delta x. That's central difference. And then at the rightmost point, the nth point, And again, in Python, index -1 is the last entry of this array. So df/dx at the last point is going to have to use a backwards difference because I don't have the next forward point. So it's the last point minus the second to last point divided by delta x. Really easy, okay? Just a big for loop, and it's going to compute all of this stuff. And notice I didn't even put in delta x here. We literally did, just for all of the f1 minus f0, we did the corresponding x1 minus x0. So we didn't even use delta x or 2 delta x. We actually took the difference of the x data. So this code technically would work even if my x was not uniformly spaced. And this would be really cool. I'd really like you to actually try to convince yourselves that even if this x data is not uniformly spaced, if it's not delta x apart, but the spacing changes, this is still going to be an accurate approximation scheme. And you can convince yourself by trying to plug in the Taylor series. There's any number of ways you can convince yourself of this. You could basically try to approximate, you could zoom into a little region where I'm going to try to draw this so that these are totally different delta x's. So, this is xk, xk plus 1, and xk minus 1. But I'm assuming that these are not a constant delta x apart. You can still go through all of that Taylor series expansion algebra and convince yourself that forward difference, central difference, and backward difference still scale with these delta x's for these differences. You can still approximate the derivatives using these schemes, even if my delta x's are not a constant. That would be a really cool exercise for you to do. Good. And actually, something I would really appreciate if any of you in the audience would like to type up a little list of the questions, the homework questions I've asked you for this lecture, and pop it into a comment. I will very likely pin that comment to the top so that everybody can see here's the homework problems for this lecture. That would be super useful for me. Good, so we've computed these, and now I'm just going to plot everything. And if we plot things, we will find that the true derivative, which we're pretty sure is going to be like a cosine function, right? Because derivative of sine is cosine, so this is the cosine derivative. And then the computed derivative, again, in these should be red x's, but I've inverted it so they're cyan x's. These are the approximated finite difference derivatives. And they're all quite accurate because I had a pretty small delta x. My delta x was like 0.1, and so all of these are going to be pretty small. Okay, so this is really cool. You actually get a really good approximation, and it's especially good in the middle because we're using central difference, but it's not terrible at the endpoints. It's actually better at the endpoints than I think it should be, and I think there's a really interesting reason why, and I hope I don't botch this, but if we remember, the forward difference and backward difference have an error. The error was something like d squared f dx squared times delta x. Okay, that was the error for forward difference and backwards difference. And so the d squared f dx squared does actually matter. Like in regions that have high curvature, high d squared dx squared, I will get more error than other regions. But notice my function was sine of x, and the second derivative of sine of x is sine of x. And so at the forward and at the first data point and the last data point of my numerical data, this is 0 and this is pi approximately. And sine at 0 and sine at pi is very close to 0. Well, it is 0. Sine of 0 and sine of pi is 0. And so at these endpoints, where my error should be higher because I'm using forward difference and backwards difference at these endpoints, it turns out that my curvature, my f double prime, is actually really, really small there. And so that's why even though I'm using a less accurate scheme at the left point and at the right point, they still look really good because they're multiplied by this really, really small number. And if you look closely, I mean, I'm not going to zoom in here, but if you look closely, I would assume that even for these central difference points, the error is going to be a little higher here because this d squared f dx squared is larger here than out here because sine is larger at pi halves than at 0 or pi. So just kind of a cool property. Like you really can get a lot of information from these Taylor series. This is really, really neat. Okay, that's actually what I wanted to show you. You could play around with this code. You can download this, try different delta x's, try a coarse grid, try a fine grid, and you'll actually see, I mean, I guess I can run this for a coarse grid. Let's see. Let's try not to mess this up. I guess I would make this coarser by changing this to 30 over 2, so that's only 15. Well, let's make it 10. Let's make it 10 data points. So instead of 30, I'm going to have it be 10 data points. It should be way less accurate because it's a way bigger delta x. Let's run that. Let's now plot my data. Ooh, it's super ugly, gross data here. And now when I plot this, well, central difference is still pretty darn good, but now I'm getting a little more error on my endpoints because of my forward difference. I'm getting a little more error. Notice this actually started at 0.1 and this ended at 3, so it's not exactly 0 and pi, so this term is not exactly 0, and there is some noticeable error there. Okay. Kind of cool. So you can try this for bigger delta x, smaller delta x. Try, you could try a second order forward difference at the left hand and a second order backwards difference on the right hand. You could try all kinds of things. Okay, I'm going to switch to MATLAB. Okay, so we are coding up this numerical differentiation scheme on these data vectors, x and f. And so it's pretty easy to do this in MATLAB. Like MATLAB is built for these kind of matrix calculations. So I'm going to create a vector from 0.1 to 3. It's almost 0 to pi. It's close to 0 to pi, but not exactly. And we're going to compute the derivative of sine of x. But instead of like the last lecture where I evaluated sine of x plus delta x like analytically, here we're just going to take a big vector of x. We're going to plug it into this function f, and we're going to have a vector of data out. So x and f are literally these vectors of data that I've drawn here. So I'm going to plot, f by x and the data. So let's just do that real quick. So this is kind of the function and the data I'm using. So all of these blue dots are these values that. So it's a pretty. You can see it's a pretty fine delta x. It's a pretty small spacing. So this is probably going to be pretty accurate. And even though this looks like a parabola, this is just one hump of a sine function from approximately 0 to pi. And now what I'm going to do is I'm going to compute all of these derivatives. But again, on my leftmost data point, I'm going to use a forward difference derivative. So that's this one here, df dx at the leftmost point at index 1 is f2 minus f1 divided by delta x. All the points in the middle for 2 to n minus 1, my derivative at a middle point is going to be the central difference, k plus I plus 1 minus I minus 1 divided by 2 delta x. And then at my rightmost point, at df dx at the nth index, it's going to be that last point minus the previous point divided by delta x. That's the backwards difference scheme. Okay? And notice I'm not actually using delta x here. I'm not actually using delta x. I'm actually using x2 minus x1 and xk plus 1 minus xk minus 1. And I'm actually using the difference in x. I'm not computing a constant delta x. Delta x could actually change in the way I've written this. I could actually have non-uniformly spaced data x, and this will still run, and this will still give me good approximations of my derivatives. This is actually a really good thing for you to check, is that if I have irregularly spaced x data that's not constant delta x's apart, but there are irregular spacings of the delta x, these are still going to be good schemes, and these will still work and approximate my derivatives. I can still approximate my derivative by the slopes of these various lines between these various points using this, and they'll have basically the same error properties based on the Taylor series. So that would be really good for you to convince yourself that this also works for non-uniformly spaced data. Okay, so I've computed all of that. Now I'm going to plot it. And that's pretty easy to do. And let's see. I'm going to make this x's for my data, just like I did before. And I'm going to make them very large, just like I did before. Good. So now the white curve is the analytical derivative, the cosine function. And these blue x's are my finite difference numerical approximation. Again, at the left and at the right, those are using forward and backwards difference, and all the points in the middle are using central difference. You might expect the points on the end to be more inaccurate, to have more error, which is almost certainly true because these are only delta x accurate, whereas central difference is delta x squared. Interesting fact, the error of the forward difference and backwards difference is not just proportional to delta x, it's also proportional to the second derivative of f with respect to x. And the second derivative of sine is also sine, it's minus sine. And at approximately 0 and approximately pi, sine is very small. So here, the error is actually going to be smaller for forward difference and backwards difference than in the middle. So kind of a cool fact. That's interesting. Okay, the central difference, its error is going to be delta x squared times the third derivative of f. And the third derivative is cosine, which is also going to be small in the middle. So it's actually going to be more accurate in the middle than at the endpoints. Interesting stuff you can get from these Taylor series, but I really just wanted to show you here how easy it is to compute these derivatives. OK, I hope you are really comfortable now with computing these finite difference derivatives for functions. So you can, if you have data or if you have a function, you can approximate the derivative, the second derivative, the third derivative, using only forward points or only backwards points or points on either side, and you can get different order accuracy for all of those schemes. So again, we'll use this later when we talk about numerically integrating a differential equation dx dt equals f of x. For example, if this is dx dt, then we could approximate that as xt plus delta t minus x at t over delta t equals f of x at t. And I could rearrange all of this and get an update rule. X at my next time step is equal to x at my current time step plus delta t times my function evaluated at x at my current time step. So this is all based on information I have now, and this is my state in the future. So you can basically step your system forward into the future one time step. Then once you have that, you can plug that in here, and you can step it forward another time step, and plug that in, and step it forward another time step. And we will basically be able to develop a numerical integrator so that if we have a differential equation, we'll be able to integrate our trajectory through that differential equation at time 0, time 1, time 2, time 3. We'll be able to numerically predict what the system will behave like. So for example, if I have a pendulum, I'll be able to start with an initial condition and predict the future. I'll be able to numerically integrate that the pendulum swings back and forth using a numerical scheme like this. So that's actually probably coming up in 2 lectures, is really taking everything we've learned here and applying it to numerical integration of ordinary differential equations. All right, thank you.